Free convection is an important aspect of heat transfer in natural and engineered systems. And a common method or mode of free convection occurs in the form of convection cells that are often called Rayleigh-Bernard convection cells or sometimes just Bernard cells. And the basic process is shown here schematically, where you have a fluid that's heated from below, and that causes the fluid to rise, and it rises and then cools at the top and sinks. And so that causes the formation of a cell. But what happens is that this circulation pattern is then repeated over here and over here, and there are three cells just shown schematically here. And if you spread this fluid out as a layer, then here's another schematic depiction of these cells where the layer is heated uniformly from above, and that causes the fluid to rise in these zones and sink in these zones. And this is manifested in many different ways, and it can be done very simply in an experiment. And here's an example of a Bernard cell where it's a fluid that was heated. It looks like just a pan from the kitchen. And you can see this cell, the fluid was rising right here in the center and then flowing horizontally and descending right here along this dark edge. And where there are multiple cells bounded by other cells, you can see that they form a pattern like this. In this case, the cells are somewhat different sizes, but if the experiment is done very carefully, you can get patterns that look like this. This is a fluid heated from below, and these are these convection cells, these Bernard cells. And if you blow it up, you can see that many of them are somewhat hexagonal in shape. So this is a nice example. These linear features are streak lines of particles that are traced in the flowing fluid. And you can see that, like this right here, this pattern it's very nicely hexagonal right in here, but you can see this circled region. Actually, this circled region isn't a very good example of what's shown here, because the circled region has this somewhat different pattern right here. And if you look elsewhere, you can see also differences in the pattern that are not hexagonal, they're more just polygonal. And then, of course, there's this one that looks a good bit different. And as we'll see, we can get many more different kinds of geometries, and the cell shapes, forms move around with time. So here's some examples from nature. This is from the space shuttle, and these are clouds, and you can see these kind of cell-like structures right here. These are convection cells, and this is another one. These are both taken over the ocean, and you can see this has a very nice, almost hexagonal shape. Well, I guess it is hexagonal here, but not perfectly hexagonal, but really quite close to it, particularly considering this is a large cloud system. Okay, so convection is occurring to form these clouds. The water vapor is rising in the center, and then it's condensing to form the clouds as it gets into the upper areas of the atmosphere. It also occurs down in the subsurface, where the crust is heated, and the mantle here is heated. That causes upward flow within the mantle, and then it's cooled here along subduction zone. This is a spreading center, the mid-ocean ridge, and so we've got a Bernard convection cell here in the mantle that is driving plate tectonics. This process also occurs in lakes, in surface water bodies, And here's some pictures of an experiment that was done where people tried to simulate the flow in a lake. And this is the experimental apparatus. They made a kind of a wedge-shaped apparatus that was clear on the side, so they could image the fluid, and they could determine the temperature of the fluid photographically. So here's a picture of this experiment where the top of the lake, this upper surface, was cooled, and you can see the dark brown color, or the brown color that's formed by cooling this fluid. And at first what you get is just a fairly even layer that's formed, but then you can see that little perturbation right there. That occurs after about 30 seconds of cooling, and you can see here's 30 seconds, these triangles, and at 30 seconds there is let's see, about 0.8 degrees C of cooling at the surface, and that extends a couple of millimeters into the below the surface. So what happens then is, with continued cooling, and you can see here are the times, little perturbations like this grow and form these cool fingers that extend down into the deeper regions, and this is the start of a convection cell. So this is downward flow, and then you'll have upward flow somewhere over here. And so you can see over the course of really fairly rapidly, over a few tens of seconds, these cells develop. And let's see, after say about a minute, here are the cells. This is going down, this is going up, down, up, down, up, down, up. And what I mean, this is somewhat irregular, but this is a real experiment, and so you would expect some irregularity. But what you see here is actually a fairly regular. The flow is broken up into these fairly regular size cells, where a cell would be, well, basically from here to here, and it's about the same size. And in fact, these Bernard cells, the width of the cell is similar to the depth. The details depend on just what the boundary conditions are. In this case, it looks like the width is a little bit greater than the depth, but generally it's about the same scale, width to depth. And so that's really dominating the fluid flow, and it will also dominate the heat flow when this process occurs. There's a dimensionless number that allows you to estimate the onset of this instability, this convective instability. The number is the Rayleigh number, and it's shown here. These are all the terms in the Rayleigh number, and it's all fairly straightforward. We've seen all these terms before. This is for a layer, and so the delta T is the temperature difference between the top and the bottom of the layer, and the layer thickness and the fluid properties. So the onset of natural convection, it depends on the magnitude of this, because basically what's happening is you have a temperature difference between the top and the bottom of the layer, and if that's great enough to overcome the viscous resistance, then this process can occur. For a layer with a top surface that's free, like a water surface, the critical Rayleigh number is about 1100. So once you reach 1100, then convection starts. So you see that the temperature difference here is in the numerator, and so as the temperature difference gets bigger, the Rayleigh number gets bigger. And if you have a layer that's of certain thickness d, and all these other things are the same, are constant, then You increase delta T until the Rayleigh number exceeds a critical value, and then you start convection. The reason why free convection happens is because fluids change density when they change temperature. And this occurs because of thermal expansion. The coefficient of thermal expansion is how the thermal expansion is characterized. And there are two different flavors of the coefficient of thermal expansion. This one, alpha L, is the coefficient of linear expansion. And basically, what that says is that the change in length of something per unit change in temperature divided by the initial length is equal to alpha. And then there's also the volumetric thermal expansion. So this is change in volume at constant pressure with temperature divided by the volume initially. That's the volumetric thermal expansion. And if you take this and multiply top and bottom by the mass and assume the mass doesn't change, then you also get the change in density with temperature at constant pressure normalized to the initial density is the thermal expansion. So in all cases, this thing has units of 1 over temperature, and you can visualize it as the volumetric change, like a percentage or a fraction of volumetric change or linear change per change in degree C or degree K. So here are some tables. This is just an excerpt of some tables, and the linear and volumetric, and there's various examples. Here's steel, for example. Steel is about 10 to the minus 5 per degree C for the linear coefficient of thermal expansion, and it's about 3 times that much for volumetric. Aluminum is even greater. It's 23 times 10 to the minus 6, or 2.3 times 10 to the minus 5. Diamond is less. Diamond is about 10 times less than steel. And gasoline is a good bit more. Now, if we go down here to water, 69 times 10 to the minus 6, or 207 times 10 to the minus 6 for volumetric. So the thermal expansion that we want to use for the density would be the volumetric thermal expansion, and it's going to be about 2 times 10 to the minus 4 per degree C. So that's a fairly small amount, but that's how much the density is going to change. And it's a fairly small amount, but that is what will drive thermal convection. So let's see an example of how to set up a problem that shows how the free convection works. So the geometry of the model looks like this. It's a slab 5 centimeters by 20 centimeters, and we're going to heat it on the top and heat it on the bottom and take a look at the effects of the heat transfer and convection when we do that. So let's see, the variables, it's pretty straightforward. These are just fluid properties, and then I calculate the Rayleigh number here. So that's really all that we're doing in the definitions. The parameters, there's this parameter D, that's the thickness, and del T that I think for our problem we'll just keep it as 1 degree K. So I used isothermal flow physics for this. There's water set up in the materials, and in isothermal flow, let's see. This is all just defaults from the materials, and you want to put in a pressure point constraint. I just use the upper left hand corner and set the pressure there equal to 0. You also need to put in volume force, and the volume force is going to be the density times g. And you need to use this density. You need to use the density from the definitions. And that's important because, let's see, this density here under the definitions is given here by this formula. And if we plot it up, we see the density here as a function of temperature. And this is what's going to drive the free convection. So we need to use that. If the density was constant, then we wouldn't get any convection. So that's all implemented here with this volume force. It's the density times g, and it's over here in the volume force in the y direction, and it's negative because it's acting downward. Okay, so for this first problem, the way we're going to set this up is just heat it on the top or the bottom. So we're going to fix the temperature on either the top or the bottom. So this is a temperature boundary here and a temperature boundary here. That's how I set it up. And what I'm going to do first is to make the top boundary the heated one. So I start off with the initial temperature is 293. The default you'll find is 293.15. I just took off the 0.15, so it's simpler to write, and so what you need to do there, I guess, is to go into initial values and make sure that it says 293. Also, the initial pressure is the initial density times g times 1 minus y. So that'll help get things going. And let's see, the first setup that we're going to want to run is where we heat this slab of water from the top. And we're going to heat it by 1 degree C, 1 degree Kelvin. And the bottom is going to be a fixed temperature. So we'll set up some particle tracing, but we'll do that. Well, I'll show you how that's set up. We've got particle tracing for fluid flow, and the default boundary conditions, the default, I think this is all just default particle properties. These are particles with that density, and this is the particle diameter, so that's 1 micron. So these are like grains of clay suspended in the fluid. And then you need to put in a drag force, and that's what's going to cause the fluid to move, or that's what's going to cause the particles to move. So we want to have that temperature. And then we need to link the velocity field here. I think the default is user defined, but you want to just put in the velocity field from this NITF2. I should point out too, when you set this up, it'll probably be NITF, and the 2 won't be there. So if you're copying things directly, just keep that in mind. And then to trace the particles through the fluid, you have to release them into the domain, and so I'll have several particles released, and I set them up with these initial coordinates. Okay, so for doing this simulation, I've tried several different meshes, and what seems to work nicely is a mapped mesh. So you get this square or rectangular looking elements here, and I set it up by controlling the distribution of elements on the sides and on the top and bottom, and then I did the mapping. So, you're going to have a trade-off between the runtime and the resolution, and so you might want to experiment around with this. Probably do it fairly coarse at first, and then make it finer to get better resolution. So the first thing that we need to do is run the fluid flow with heating, and so I've got the set up so I can view the results. And fluid, we're heating it from the top by 1 degree, and this is the time here in seconds. So where temperature is increasing, it's propagating down. And so we've seen this kind of pattern before. This is what you expect to get when you heat something by conduction. The heat propagates in, it makes this nice uniform band, and it's going as the square root of time, and so it's propagating in, but the longer it goes, the slower the front goes, propagates in. And so we run the 100 seconds, or I guess maybe 200 seconds, and get this pattern. Let's take a look. Let's take a look at the temperature first. So there's the temperature at the end, and pretty much just driven by the convection or conduction. If we plot the velocity, then you can see actually that there is some velocity. The highest velocity is right there, and but take a look at the units here, 10 to the minus 8. So there is some velocity, but it's really small. And what's happening is we're heating up this layer of water, and it's expanding, and the thermal expansion causes the fluid to flow. Very small amount. Okay, so that's the heating, and then we can do particle tracing by going here to a separate study. You need a different solver to run the particle tracing, so I set that up separately. The particle tracing uses the fluid velocities that we just calculated. So under the drag force, we link the drag force to the fluid velocities that we just calculated there. So when we set up the study, we need to also link them, and that's done right here under values of variables not solved for. It's study 3 that has the fluid flow results in it. Okay, so I just ran those particle trajectories, and here they are. The way I set this up, the display is set up so that the color, I use this expression here, where, see where it says color expression, is the y coordinate at time equals 0. That's what that expression means. And so these are the particles, and if I zoom in, I can see there are a bunch of them side by side. And let's see, this is, well, here's what they look like at the beginning. And 200 seconds later, here's what the particles look like. So, not a whole lot of movement. So we've heated this from the top, we've heated the fluid by conduction, and the movement of the particles that we've seen is, well, I couldn't see any movement at all. I guess they moved a little bit, but not really, so it shows up. Okay, so let's see. Let's go ahead and change this. I'm just going to change the boundary condition. So we're going to heat it by the same amount, 1 degree. So del T is just going to be added to the lower boundary condition now. So it's right here, and we'll go and just repeat what we've done. Okay, so we rerun the fluid flow, and you can see it's heating it by conduction, and we're getting the same kind of layer. But now the Rayleigh number is increasing, and now we've started to form some free convection. It rises and flares out, and you can see the color is decreasing because as it rises, it cools. This hot blob cools and basically transfers the heat into the cooler fluid, and you see we get this kind of um, crazy looking pattern where these columns of hot fluid are moving up and causing this swirling pattern. And here, this is actually one of these Rayleigh-Bernard cells, uh, up here going and descending like that. Okay, so let's take a look at the temperature. This is the temperature at the end of the simulation. And we can see the cell right here and another one. And you can see the fluid looks like it's trying to come up here. So there are, I don't know, two cells, but I don't know, this looks like it might be a cell here and another one trying to come up. But in general, what we saw was this was a very dynamic, very transient type of system. And so it was constantly changing during the simulation. So let's take a look at the video, and I'm gonna have to. It's gonna have to run by itself the whole time one time through before I can slide it back. So we run about 30 seconds and nothing much happens, and then you can see the instability starts here near the ends, and it starts out with this one growing, and then we have a couple more, two of them that are symmetric here on the inside start growing, and then another pair here also on the inside of the last one. So there's the first one, there's the second one, there's the next one, and what's happening is they're rising, and then there's also a flow from right to left or from inward to outward that's pushing these little convecting cells out towards the edge. So that's the pattern that develops here, and that keeps happening. These convection cells get kind of smeared over and pushed up against the wall. You'll see this one and this one will get pushed over there, and so new ones are forming, and they're getting then compressed over against the wall. So we've got a lot of heat coming up here and then coming down in the center. So it seems like the overall pattern is that we've got a fairly symmetric situation, but we'll have the heat column starting to grow as it increases in amplitude. It also moves laterally over to the edge. So we've got this large scale circulation pattern forming. So that's really, I think, a remarkably complicated flow system that forms from really just a fairly simple geometry, simple heating system, and it's obviously completely different than what we get when we heat this from the top, and that's because this heating from the bottom is unstable. Okay, so when I first did this, I thought, well, 1 degree, that's a pretty small temperature difference. But if we go ahead and calculate the Rayleigh number, I set up this global evaluation to calculate the Rayleigh number, and the Rayleigh number is actually 1 times 10 to the 6th. So what that means is that the Rayleigh number is here. So If it's basically 1,000 times more than what you need for the onset of convection in this system. So we had 1 degree of temperature change. We could reduce that to 1,000th of a degree of temperature change, and we would still be able to meet this critical Rayleigh number. So the implication there is that this process of convection can happen with really very small temperature differences. So I wanted to compare these two analyses where we heat from the top or heat from the bottom in a couple of other ways. And so I used this function here to calculate the boundary heat flux. And so what that is a integration along the line that is the upper or lower boundary. And so I put that in and then selected the lower boundary and the upper boundary and calculated the heat flux. And here's the total heat flux and plotted that up. And that's shown down here, the heat flux across the boundary. And the way this works is that an inward heat flux is negative, outward heat flux from the boundary is positive. So the first analysis that I did was for heating the top. Basically, that's the first analysis that we did. And if you heat the top and hold it at constant temperature, then the heat flux is shown here with this blue line. And so it's initially minus 360s, and so that's it's an energy flux, and it's going into the slab. And the heat flux then decreases with time. And finally, at the end, it's about minus 60. Okay? Then these two curves are the heat flux. Well, okay, let me also say this is the upper surface. The lower surface, when I heated from the top, I also did that, but it's essentially zero. So it plots up here. So when we heat from the top for 200 seconds, there's no heat flux at the bottom. Okay? And so if we do the same thing when we heat from the bottom, here's the heat flux from the bottom. And what you get is that for the first 40, 50, say 50 seconds, essentially it's the same as the heat flux for convection or conduction. Essentially the blue and the red are the same. And what's going on is that we haven't really had convection start in any appreciable way at up till 50 seconds. But then what happens is, so basically what's going on here is the heat flux is high, and then it's decreasing, and then at this point the convection starts, and we start to have heat being moved from the boundary into the slab by convection, in which case the heat flux comes back up again and then reaches a maximum, and this is a maximum negative number here after 120 seconds, and then it tails off again. So this difference here is the heat flux that is occurring by convection, by that fluid movement that is induced by the temperature difference. And the other consequence is that the top part of the top boundary also is starting to see some heat flux after about 90 seconds. So this is the upper surface, and what happens is that this is the onset of convection right here, and then about this is about 40 seconds later, the heat is starting to arrive up at the upper surface, and we get heat flux up at the upper surface increasing. So that's I think that makes sense with the pattern of how we saw the temperature changing. One of the implications, actually, where this shows up in in everyday life is, let's see if we go back here to the slab. If this slab here is meant to insulate, um, so you want to keep heat from moving through it, then you would use a low thermal conductivity material to keep the conduction low. Air, as it turns out, has pretty low thermal conductivity, but the problem is if you have a layer of air that this natural convection occurs, and the natural convection transports heat, just like we see here, and like we see the elevated heat transport shown by these graphs. And so that's why just a gap of air uh, is not the greatest of insulators. But if you can cut off and prevent this free convection cell from forming, then air actually is a pretty good insulator. And so what's done then is to put in material that is very low density and has a lot of air trapped in it, but the air is in some small cells, like little cells in styrofoam, or in between the pieces of fiberglass. And so essentially what happens is the insulation, the solid part of insulation that we use, is the solid part doesn't really conduct heat very well, but it's the air that's really doing the insulating. What the solid part does is prevent the air from convecting and transferring heat by convection. So another thing that we can do is calculate the heat that's stored in this block. And the way I did that was to use this integrated over the area, and what I integrated was this term right here, which is the internal energy, essentially the temperature times the heat capacity. And so what I was interested in is how the stored heat changed. So I took the internal energy minus the internal energy at time equals 0. And I integrated that over this region, and that gives me the total energy that's stored. And so I calculated that for these two different methods of heating, well, the two different geometries of heating. If we heat the top, then the energy stored looks like this. And if we heat the bottom, then the energy stored looks like this. And we see that up to about 60 or here 70 seconds, we have about the same result. And then as time goes on, when we heat the bottom, this convective process allows us to put more heat energy into this block of water. So there's one more thing that I want to show you, and that's this particle tracing. So we're just going to calculate this for the heating scenario that we've just set up, where we heat this region from the bottom. And we saw when we did this before that essentially there was no fluid motion when we heated it from the top. So when we heat it from the bottom, we are expecting to see a little bit more fluid motion. And here's the simulation. It takes a good bit longer to do this calculation than it did before. So there's a preview of what the particles are going to look like. So let's go and turn back the clock here to the beginning. So this is how things are starting out, and basically the color code is the elevation in the layer. And so if we advance in time, you can see, I guess it was what, like 30 seconds, and not much is happening. 30 seconds, maybe it was, yeah, I guess it was like 50 or 60 seconds before we started to have those crossovers. So there at 50 seconds we see a little bit of convection right on the edge. That's consistent with what we saw previously. So we go to 60 seconds and we start to see some disruption of the particles, and the edges here are rising. We can see a little bit of a convection cell forming right here where these particles are going down and this is going up, and it's moving some more. So really the action is starting at the edge and moving in. The fluid is here is still stable after 90 seconds, and this is now getting really pretty well mixed, and it's moving inward. So let's see, after 120 seconds, starting to get a good bit of mixing, and it's stable here. It's just a small amount of motion here at the edge. And so we can plot this a couple of ways. We can also put a line on connecting, or basically a line tracing out these particle velocities, particle paths, and that looks kind of interesting, but it also gets pretty complicated. So if we, okay, let me do that. Let's go and look at it at a earlier time. So after 70 seconds, we've had some motion. Yeah, so here you can see traces out the path, and it gives you I guess a little better sense of how the particles are moving. But in here where we really have a good bit of motion, things are getting pretty complicated, the flow paths. Okay, and so then if we run this all the way out, we can see that indeed we have a pretty well mixed system by 200 seconds.